We're going to continue by introducing an artist. Her name is Zaire Former. So, Foreman, she used large-scale compositions of melting glaciers, the icebergs floating in glassy water and waves, crusting with foam, explore moments of transition, turbulence, and tranquility. You can search her and watch her discussion, the meditative process of artist creation and the motivation behind her work. She said, "My drawings celebrate the beauty of what we all stand to lose," she says. "I hope they can serve as records of sublime landscapes in flux." Okay, during the past before present BP. So, which refers to radiocarbon dates determined by the decade of carbon-14 in organic matter, including charcoal. The reference date used is 1950. Carbon-14 has a half-life of 70 years, meaning that half of the initial amount has decayed in that time interval. Typically, there will be a series of dates for a given core to bracket different climatic phases. Radiocarbon dating can be applied back to about 50,000 to 60,000 years. Dating of older materials is usually performed using uranium and thorium isotopes in corals. For example, 234U has a half-life of 245K and 230TH of 75K. Fresh water is less dense than seawater and so forms a stable upper layer in the ocean, preventing vertical overturning. A contributory effect of the freshwater influx would have been the increase in sea ice cover, since that water freezes at 0 degrees instead of the negative 1.8 Celsius for seawater. During the last glacial cycle in Africa, there was a cold, arid phase about 70 Ka, followed by a slight climatic amelioration and then a second aridity maximum around 22 to 13 Ka. These arid phases coincided with extensive glaciation in more northern latitudes. Conditions then quickly became warmer and moister, leading up to the Holocene optimum of greater rainforest extent and savanna vegetation covering the Sahara, with high lake levels from 9,500 to 6,500 before present. This allowed the expansion of population into areas of North Africa that are now desert. Conditions then turned much more in around 5,500 BP in the Sahara and the Thar Desert of northwest India, becoming similar to the present. The start of the Holocene past glacial time is now dated to 11,700 BP, although the final Scandinavian ice sheet disappeared only 9,000 years ago. In the Laurentide, about 65,000 years ago, the final remnant of the Laurentide ice sheet appears to be the present-day Barms ice cap on Baffin Island. Pollen records from lakes and peat peat bogs that allow reconstruction of the vegetation, beetle assemblages that indicate microclimate, and packed rat middens in North American desert environments that contain plant remains provide evidence of Holocene paleoclimate on continental time scales. Annual time scales can be resolved from annual growth rings in trees and corals, as well as annual layers in shallow ice core from the major ice sheets and tropical mountain ice caps. Conditions during most of the Holocene were much less variable than during the glacial periods. Thermal maximum conditions, the hypothermal, are dated to 8,000 to 5,500 BP over much of the globe, but around 9,000 BP in high latitudes away from the remnant Laurentide ice sheet. The thermal maximum is attributed to increased solar radiation receipts resulting from the occurrence of perihelion, Earth closest to the Sun, in July 10,000 years ago rather than January as at present. This made boreal summers warmer than now and go up to 5 degrees warmer in northern and southern high latitudes. It also led to enhanced monsoonal circulations in South Asia and West Africa as a result of the warmer land masses. Between 10 to 8 K and 7.3 to 6.4 K, Mag Lake, Chad, and in Western Africa covered an area of 350,000 square kilometers between 11 and 18 degrees north, compared with 1,500 square kilometers in 2000. This warm interval has followed by a cooling trend with neo-glacial periods, episodes of glacial readvance, notably during the Little Ice Age, dated to AD 1550 to 1850 in Europe and around the North Atlantic, or AD 1400 to 1700 for the Northern Hemisphere as a whole, according to Mann et al. Temperatures were about half degree to 1 degree Celsius below those at present, but fluctuated widely on decadal timescales. The Little Ice Age succeeded a brief mild interval known as the medieval warm period or medieval climate anomaly around AD 950 to 1250. Temperatures were about half degree to 1.4 degrees Celsius above those of 1961 to 1990 for the northwestern and central North Atlantic, the southern United States, and central China. During this interval, the Vikings sailed the North Atlantic and built settlements in southwest Greenland that later succumbed to the deteriorating climate. The general pattern of hemispheric temperature over the last millennium is here, if you look at this picture. So the trend ensembles a hockey stick by Michael Mann. So he updated Michael Mann, then with an abrupt rise at the end, so that you can see abrupt at the end. If you watch Michael Mann's a lot of YouTube videos, he will talk about his hockey stick. Over the last 1,000 years, there have been persistent dry periodic lasting up to several decades over North America, West Africa, and East Asia. These historical droughts are linked to tropical sea surface temperature variations, with La Nina-like sea surface temperature anomalies in the tropical Pacific often leading to widespread drought in North America, according to Des et al., and El Nino-like sea surface temperature warming in the Pacific causing drought in eastern China. So the Maunder minimum roughly coincide with the middle part of the Little Ice Age, during which Europe and North America experienced colder than average temperatures. Whether there is a causal relationship, however, is still controversial, and no convincing mechanism for the solar activity to produce cold temperatures has been proposed. And the current best hypothesis for the cause of Little Ice Age is that it was the result of volcanic action. The onset of the Little Ice Age also occurred well before the beginning of Maunder minimum. Comparison of group sunspot numbers top. It's right here. And then central England temperature CET and observation middle, and reconstruction and modeling of North Hemisphere temperature. In HT, the CET in red are summer average for June, July, and August, and in blue, winter averages for December of previous year, January and February. Northern Hemisphere temperature in gray is the distribution from basket of paleoclimate reconstructions, darker gray showing higher probability values, and in red are for model simulations that account for solar and volcanic variations. By way of comparison, on those same scales, the anomaly for modern data after 31 December 1999 for summer CET is plus 0.65 Celsius degree. For winter CET is plus 1.34 degrees Celsius, and for North Hemisphere temperature is 1.08 degrees Celsius. So some spot data are in supplementary data too in central England. Temperature data are as published by UK Met Office. The North Hemisphere temperature data are described in later IPCC-AR5 report of working group. So, other likely causes of climatic variations over the last millennium: fluctuations in solar output and volcanic activity. Solar output across all wavelengths varies about 0.1% over the next less than 11-year solar cycle. In 1976, Jack Addy identified the near absence of sunspots from 1645 to 1715, the so-called Maunder minimum, as a potential cause of the LIA, Little Ice Age, a hypothesis that was later largely accepted. Solar output is increased during sunspot episodes due to the increased emission from the brighter solar facula, which outweighs the decrease from the darker and cooler sunspots. During the Maunder minimum, which coincided with the middle of the Little Ice Age, there was a prolonged absence of sunspots. However, it is not known how much total solar radiation decreased during that time. Estimates vary from less than 0.03% to as little as 0.1%. There is debate too as how the solar cycle affects global temperature. One theory involves top-down effects via stratospheric zone. Another suggests bottom-up effects on evaporation over tropical oceans that are transmitted to the troposphere via latent heat in convection.